Today, we're going to build a blueprint, but not for a building. We're building a blueprint for understanding AI progress itself. We're going to cut through all the noise and really look at how AI develops, not as just this random series of breakthroughs, but as a structured, understandable process. And we're going to do it by synthesizing 4 really important research papers.
So let's just get right into the big question, the one you hear everywhere, right? Is AI this unstoppable rocket ship of hype, just exponential growth forever? Or is it about to smash headfirst into some really hard theoretical limits? I mean, which one is it?
These two ideas pretty much frame the entire debate. You've got the pure hype camp who see this smooth, accelerating curve heading straight for superintelligence, where, any problem could be solved with just more data and more compute. And then you have the hard theory camp who argue we're just banging our heads against the unbreakable walls of computer science, and that any real progress is basically an illusion.
But what if both of those stories are missing the point? The research we're diving into today suggests the answer isn't a simple either-or. Instead, it reveals this really coherent framework, a blueprint, if you will, that explains how AI makes real structured progress while still totally respecting those hard theoretical limits.
Okay, so the first half of our blueprint is all about laying the formal foundation. We're talking about the absolute rules of the game, the ones set down by decades of computer science. This first pair of papers, they're going to establish the outer walls and the inner frontiers of what's even possible.
So to even begin to understand the limits, we have to go all the way back to Turing's original idea of what a computer is. Mechanization isn't just a fancy word for automation. It's a very precise concept. It means taking some complex process and breaking it down into a finite set of simple, local rules that a machine can follow, no questions asked. This right here, this is the bedrock of all computation.
And here is the first major insight. See, if intelligence was just one giant fixed set of rules, we would have solved it by now. But it isn't. The whole idea here is that once we successfully mechanize a task, that creative, human work of guiding the process, it just reappears one level up at a higher abstraction. So progress isn't about finding some final ultimate algorithm. It's this constant process of building new layers on top of old ones.
This visual shows that cycle perfectly. Imagine you're at any given stage. Let's call it a sub-n. There's a set of problems you can solve. But there's always a boundary, right? An edge where you find problems that are just unsolvable from within that layer. So how do we make progress? We build a new layer, a sub n plus 1, that manages to mechanize a task that was just out of reach before. But by doing that, we just create a brand new, higher level boundary. It's this perpetual upward climb.
So that process defines the absolute outer wall, the line between what's computable and what's fundamentally uncomputable. But for most things we care about, that wall is infinitely far away. So the second paper in this first pair asks a much more practical question. Okay, inside the massive realm of what's technically computable, what can we actually solve in a reasonable amount of time?
And this brings us to the polynomial hierarchy. Now, I know it sounds super technical, but don't get lost in the jargon. The best way to think about it is like a ladder of difficulty. At the very bottom, on the first run, you have P. These are the problems we can solve directly and fast. Go up one rung to NP, and you have problems where if I just hand you an answer, you can check if it's right really, really quickly. Think of checking a winning lottery ticket. Each step up this ladder represents problems that get harder and harder, where even checking an answer needs help from the level below. It's our map for this staged climb in problem-solving power.
All right, so let's put pair 1 together. On one side, you have the outer boundary set by pure computability theory. This is the absolute hard limit. It's what no rule-based system can ever do. Then, on the other side, you have the practical, inner boundary defined by feasibility. This is the line that separates problems we can realistically solve from those that, are technically solvable but would take longer than the age of the universe. This is the playing field where AI actually operates. So, we've got our map, we have the theoretical boundaries, but a map doesn't explain the car. And that's where our second pair of papers comes in. This is the practical engine. The real-world empirical forces that are actually pushing AI forward inside that feasible space. And in the process, they're completely reshaping the computers we build.
The first part of this engine is the scaling law, and this is an absolutely crucial observation. For a lot of AI models, their performance gets predictably better the more compute you throw at them. The error rate, what we call loss, goes down as a power of the compute you use. Why is this so huge? Because it turns progress from a guessing game into an engineering problem. It gives us a predictable, even if it's diminishing, return on our investment. But of course, there is a catch. That curve shows diminishing returns.
To get the same little bit of progress, you need to pour in more and more and more compute over time. So, how does progress keep going? Well, this chart reveals the secret sauce: hidden efficiency. Progress in the real world isn't just about that blue line. It's about how fast we get better at everything else: our algorithms, our software, our hardware. The real race isn't just to add more GPUs, it's a race for efficiency that lets us move along that curve faster than the curve is flattening out.
So the key takeaway here is pretty counterintuitive. Diminishing returns don't actually stop progress. In fact, they're the primary motivation for it. This rising operational burden, the fact that it gets more and more expensive to get that next bit of performance, is exactly what forces us to be relentlessly innovative in our systems, our algorithms, and our architecture. It's the pressure that fuels the whole shebang. And that pressure has a very real effect on the machines we build. To get it, the fourth paper gives us this awesome concept: the value scalable workload, or S. Now, this isn't just about what you can run in parallel. It's about the part of a task where adding more compute actually creates more value. We're not just talking faster results, we're talking better results, higher quality images, more coherent text, totally new abilities. And in modern AI, S is getting massive.
And that leads to this really powerful quote, which is right at the heart of what you could call a modernized Amdahl's law. For years, we built specialized fixed-function computer chips to do one thing really, really well. But this quote just nails the new reality. As the valuable part of the AI workload becomes this giant, ever-changing, ever-expanding thing, that rigid, specialized hardware has to constantly justify why it should even exist when compared to more flexible, programmable hardware like GPUs.
This chart shows you exactly what's happening. When that value scalable workload S is low, yeah, it makes total sense to spend most of your hardware budget on those specialized fixed chips. But as S gets bigger, as more of the work that actually creates value becomes dynamic and scalable, the whole strategy flips on its head. The budget shifts, and it shifts dramatically toward general, programmable hardware that can actually adapt to this moving frontier of what's valuable. This is the economic force that's driving the entire programmable hardware revolution we're living through.
Okay, so we've laid out the boundaries and we've fired up the engine. Now it's time to put all the pieces together and look at the completed blueprint for AI progress. And remember, it's not a final map to a destination, it's a description of the journey itself. And here it is, our four-part framework. So you've got the first paper giving us that outer boundary, the absolute uncrossable line from computability theory. Then, the second paper defines the inner boundary, that frontier of what's actually feasible. Next, the third paper describes the empirical engine, the scaling laws that reliably convert compute into new capabilities. And finally, the fourth paper shows us the architectural response, how that engine's pressure physically forces our hardware to become more general and more programmable.
So, what's the big idea at the end of all this? It's that AI's trajectory isn't some kind of magic, unpredictable force. And it's definitely not just hype. It's a structured, deeply principled, and yet totally open-ended process. It has formal limits, for sure, but it also has this incredibly powerful engine that drives this constant, layered climb within those limits. And that engine literally reshapes the tools we use to think. This framework gives us a much better lens for understanding how we got here, doesn't it? It replaces that chaotic screaming match between hype and impossibility with a structured, coherent explanation. But really, the most exciting part is looking forward. If this really is the blueprint for how progress works, what does it tell us we should be trying to build next? What is the next layer that's waiting to be mechanized?